So we're going to talk about the last topic for today's lecture is the constraints in static determinancy. So in certain cases, bodies may be supported by more constraints than is necessary or by improper constraints. So in some cases, what we'll have is that the number of unknown forces and moments may be greater than the number of equations that we have. So the number of equilibrium equations. So when that is the case, we consider a problem to be statically indeterminate. Right? So I'm going to give some examples of some statically indeterminate cases. So at first we have a few examples. So for this example, on the left-hand side, we have a beam that's attached at point A by a fixed connection. All right, so we're going to draw the outline of the beam first. Then we'll draw our external forces and moments. So we have a 2 kilonewton moment applied at point A. We have a 500 newton load applied downwards at in between points B and C. And then we're going to apply our reaction forces and our reaction moments. So for a 2D case, we have a fixed connection at A. So we'll have a force in the x direction, a force in the y direction, and a moment in the along the z-axis. All right, and then for at B, since we have a normal roller, we can say we'll have a normal reaction at B, and at C we have another roller. So we can say this is N C. All right, so in this case, since it's 2 dimensions, we have at most we have 3 equilibrium equations. All right, we have the sum of the forces in the x is equal to 0, the sum of the forces in the y is equal to 0, and we have the sum of the force in the sum of the moments about the z-axis have to be equal to 0. So in this case, we have our number of unknowns is going to be 1, 2, 3, 4, 5. All right, so we have 5 unknowns. Since we have 5 is greater than 3, our condition up here. Therefore, this problem may not be solved using statics, all right, or using the equilibrium equations. All right, so the second example we have here is we have a rigid body that, so I'll draw its outline out here. So we have a rigid body, which is a rod. Right, at point B, the rod is inserted into a wall, which would be considered a fixed support. At point A, we have a journal bearing. All right, so we can say we can define our XYZ coordinate system here. All right, and then the second step would be for us to define, or the next step would be to define the external forces. So we have a 400 Newton force applied along the negative x-axis at that joint, and then we have a 200 Newton force being applied along the negative z-axis at that bend in the pipe system. And then the next step is to include all of our reaction forces and moments. So at a fixed connection, we're going to have a lot of different, we have 3 forces, right? And then we also would have 3 moments. So I'm going to draw the moment about the x-axis at B, the moment about the y-axis at B, and the moment about the z-axis at B. All right, and then we have at A we have a journal bearing. So for a journal bearing, it can move along this axis and it can rotate about that axis as well. But every other motion would be restricted. But since it's connected at another point, we can not have to include the couple moments. So we'll be left with A of y and A of z. All right. So that is our free body diagram for this system. We have, in this case, we have 6 unknowns at point B, and we have 2 unknowns at point A. So we have 8 unknowns, and we have, for 3D problems, we have 6 equilibrium equations, so we'd be unable to solve this problem as well. So this would also be statically indeterminate. So in MME 312, you will learn how to solve these problems. So you will learn how to solve these problems. But for now, you will ignore these problems. All right, so if you get this condition where you have more unknowns than the number of equilibrium equations, check the assumptions you make in your free body diagram to make sure that is the case. But if that is the case, you should stop working on the problem and not continue, because you will be unable to solve the problem based off of the information that you were given. All right. So the second type of problem that you could run into is that you could have a rigid body that is improperly constrained. So for this example, we have a few sets of rigid bodies. So if we draw the free body diagrams of each of these, what we'll notice, so on this case here, we have a pin at A, we have a smooth roller at B that's connected on the right-hand side of the beam, and we have a force that's being applied along, like, has an X and a Y component to it. So we draw the external force first. All right, we can also draw our coordinate system here. All right, and then we would draw our reaction forces. So we have at A we have a pin, so it will have a force in the x direction and a force in the y direction. And at B we have a roller, so it would have a force that goes normal to the contact. In this case, it would be going along the x direction. So the issue with this this system is that if you sum the moments about point A, they would not equal 0, since P would create a moment, and NB would be unable to create a moment. The reason that NB cannot create a moment is it goes along the same direction, or it goes through point A, so it'd be unable to create a moment about that point. Right? So for the next couple of cases we draw out our free body diagram. All right, in this case we have 2 ball and socket joints here. So we're going to just draw out the shape of our rigid body. We'll define our XYZ coordinate system. We'll apply our external force. And we'll apply our reaction forces. All right, so we have at A, we'll have 3 forces, AX, AY, and AZ. At B, we would also have BZ, BX, and BY. All right. The issue in this case is that this force here would create a moment about this axis, and neither of these supports would be able to support that moment. So we would rotate about this axis. So we'll say that P create a rotation or an unbalanced moment about the AB axis. Therefore, the rigid body AB is not constrained or improperly constrained. All right. And then in this part here, all right, we can draw out our rigid body again. So if we do that, all right, we have, this is a 2D example. Here we have a force P that's applied. It has an X and a Y component. And then we have two rollers, one at A, and we have one at B. All right, and if we look at this equation, if we look at the equilibrium equations, we'll see that the sum of the forces in the x direction were not equal to 0 because P of x is the only x component. All right, so again, we have an improperly constrained part. All right. So if we go to the next page, we'll see a few more of these. All right. You can feel free to stop the video at any time and see whether or not you can determine how these are improperly constrained. These examples are improperly constrained. All right. So in this case, all right, you have a rigid body. I'll say it's in 3 dimensions, so we'll define our x or y on a z-axis. It has 3 pulleys that are attached to it, or 3 cables attached to it at point A, point B, and point C. They would each, you could say they would create a reaction force, which was labeled as TA, TB, and TC. And then we have an applied force of 100 newtons here. All right, and that 100 Newton applied force is going along the negative x-axis, and the components of TA, TB, and TC are going only in the positive direction. So the sum of the force in the x direction would be equal to 100 newtons, which does not equal 0. Therefore, we would have an improperly constrained part, right? So it would not be at 0. All right, and then our next case here is we have a rigid body where we have it's connected at pins at the 2 ends. But if we look just at A and B here, what we'll see here is that when we draw our free body diagram of AB, all right, we'll have a 100 Newton force that is acting along in the negative y direction. All right, and then we'll include our reaction forces. So we have a pin at A and a pin at B. So at A, we'd say AX, and we have AY, and then at B, we would have a BX and BY. Now, from last lecture, we talked about 2 and 3 force members. So if we look at, we can use the rules of 2 and 3 force members to simplify this problem down. So if we look at the problem, the section of the beam from point O to point A, here, what we'll notice is we have a force due to the pin at point A. All right, so we would have so we have OX and we have OY, and then at this point here, we would have AX and we have AY. But what you'll notice is that there's only two forces acting on this system. So for two forces, we know that the forces have to be equal in magnitude, opposite in direction, and they must go through the points where the force is being applied. So for OA, this would simplify down to just being a single force going along the x-axis, all right? So we could write this like this. So therefore, we can remove or get rid of one of our components. Oops. All right, and we would be left with just A force along the x-axis. All right, and then the same thing we could do with the other link. So we end up with a force at point B that would also go along just the x-axis. So in this case, we have no force that would be going along the x-axis, so we could say that the sum of all the forces in the y direction would be equal to negative 100 newtons, which is not equal to 0. So we would have an improperly constrained part. All right. So that concludes this this video, and we have one more video to go for this lecture.